All right, let's just get right into it, shall we? Welcome to this explainer, where we are going to completely demystify the invisible infrastructure that is powering our modern, hyper-connected world. We're going to take a really close look at the fascinating architecture that allows everything from your morning emails to your late-night streaming binges to function so flawlessly. I mean, really? Think about it for a second. How did this very explainer actually reach your screen? It might feel like absolute magic, but it's actually a highly structured, fiercely logical system routing data all across the globe. We totally take it for granted, but right under the surface, it is a massive triumph of engineering and standardized rules. So to really wrap our heads around this, we're going to build the internet from scratch today. We'll quickly hit the basics of networking, look at the different types of networks, and then dive into the physical topologies and transmission media that actually string them together. After that, we'll trace the evolution of the internet itself, figure out the crazy mechanics of how data actually moves, and wrap up with IP versus MAC addresses. Okay, part 1, the basics of networking. Because before we can understand the entire globe, we really need to understand the room. So what exactly is a computer network? Well, at its core, it's just a group of autonomous, independent devices connected together so they can share information or resources. Whether you're beaming a video from your smartphone to your TV, or linking up gaming consoles, or, connecting a laptop to a server in Tokyo, it literally all comes down to independent devices communicating using a shared set of rules. Now, obviously, there is a massive trade-off here. All this connectivity brings huge advantages, right? Sharing hardware like a single office printer is way cheaper, and you can centrally manage software updates. But there's a catch. It's a double-edged sword. If that central network isn't managed properly, the whole system gets super unstable. Plus, the absolute second you connect devices together, you are opening the door to security risks and external vulnerabilities. Moving right along to part 2, types of networks. Now that we know what a network is, how do we organize who does what? Based on the roles these devices play, we primarily see 2 different setups. First up is peer-to-peer, or P2P. These are usually small setups, maybe a handful of computers where every single machine acts as both a client and a server. There's no big boss, no central control. They are super cheap and easy to set up, but kind of hard to secure. On the flip side, we have client-server networks. In this master-slave dynamic, a powerful, dedicated central server handles the resources, the security, the backups, and the dependent client computers just access it. It gives you far better performance, but beware, if that central server crashes, your clients are completely stranded. But we can also scale these networks geographically, which is pretty cool. It starts super small with a PAN, a personal area network, reaching maybe 10 meters. Think Bluetooth linking your phone to your wireless earbuds. Then we step up to a LAN, a local area network, covering up to a kilometer, like the Wi-Fi in your house. Next is a MAN, a metropolitan area network, spanning 30 to 40 kilometers for things like citywide cable TV. And finally, we hit the WAN, the wide area network. There is literally no upper limit here. It spans entire continents, and the absolute largest WAN in existence is the magnificent beast we call the Internet. All right, part 3, topologies and transmission media. As we start connecting thousands of devices, the physical shape of the network and the actual cables we use become absolutely critical engineering choices. When we talk about topology, we're talking about how a network is physically laid out. A star topology, for instance, connects every single node directly to a central hub. It is wildly common because it's incredibly easy to manage. But again, if that hub dies, the whole network goes down with it. Then you have a bus topology, where every node just attaches to one single linear cable called a backbone. Super cost-effective, sure, but diagnosing a fault is a nightmare, and packet loss can be pretty high. Then things get a little more creative. A tree topology cleverly mashes up the star and bus layouts to create this scalable, hierarchical flow, which is perfect for massive corporations. A ring topology, on the other hand, connects every node to exactly 2 neighbors. Data passes in a single direction around the circle, kind of like passing a token. It guarantees equal access without needing a central hub, but, and it's a big but, one single cable break brings the entire ring to a grinding halt. Now, to physically wire up these shapes, we use what's known as guided media. The most basic is twisted pair. By literally twisting copper wires together in a double helix, we cut down on crosstalk, or signal bleeding. It's cheap, but it tops out at about 100 meters. Then we have coaxial cable, a solid wire core surrounded by a shield, which can push data up to 500 meters and is a staple for broadband. But the undisputed crown jewel? Fiber optic cable. This stuff transmits data as literal pulses of light through microscopic strands of glass. It is completely immune to electrical interference, it's highly secure, and it supports insane bandwidths of over 100 gigabits per second. You are, quite literally, communicating at the speed of light. Which brings us to Part 4, Evolution of the Internet. So how did these isolated, physically cabled networks snowball into the global powerhouse we use today? Well, the story starts back in 1969 with a U.S. Department of Defense project called ARPANET, and honestly, their goal was just to connect computers at a few different universities. By the mid-'80s, the National Science Foundation spun up NSFNet, which was a high-capacity network strictly meant for academic research. Private businesses weren't allowed on it, so what did they do? They built their own networks. Eventually, ARPANET, NSFNet, and all those sprawling private networks just linked up with each other at peering points, and boom, you have a worldwide network of networks, the Internet. Part 5, Moving the Data. So with this massive global infrastructure locked in, how does a message actually travel from your laptop to a server halfway across the planet? To move data efficiently at this scale, engineers had to completely rethink communication. Traditional telephone networks used circuit switching, right? Where one single dedicated physical copper wire is locked down between you and the receiver for the entire phone call. But the modern internet, it brilliantly uses a totally different revolutionary technique called packet switching. Here is the absolute genius of packet switching in practice. When you send a file, the Transmission Control Protocol, or TCP, chops your message up into tiny little blocks called packets. Every single packet gets a serial number and a destination address. And instead of reserving one dedicated path, these packets are just fired across the globe through any route that's available. Imagine tearing up a letter, mailing every single scrap in a separate envelope, and having them all magically piece themselves back together at your friend's house. They might arrive completely out of order, but TCP just reads the serial numbers and meticulously reassembles the whole thing. It is incredibly robust. Finally, Part 6, IP versus MAC addresses. With billions of these little packets flying around simultaneously, how do they know exactly where they're supposed to land? Just like a house needs a street address, every device gets a logical internet protocol, or IP address. This is the GPS that routes packets from one network to another. The classic format we all know is IPv4. It uses a 32-bit format, those 4 numbers separated by dots, and it gives us about 4.3 billion unique addresses. But because we literally put the internet into everything nowadays, we're transitioning to IPv6, which is a massive 128-bit system using hexadecimal numbers. This creates so many unique addresses that we could assign an IP address to every single atom on the surface of the Earth, and we still wouldn't run out. Crazy, right? But here's the kicker. While your IP address is logical, meaning it changes depending on where you are, like moving your laptop from a coffee shop to your living room, your hardware also has a permanent, physical 48-bit address known as a MAC address. This media access control address is hardwired straight into your network card by the manufacturer. So basically, the IP address gets the data to the correct local network, but the MAC address actually hands it off to your specific physical device on that network. Getting a grip on this foundational architecture is absolutely vital, especially when we look at where we are heading next. We're rapidly moving toward a fascinating, multi-dimensional vision of tomorrow known as the inner space, a technology that is completely poised to replace flat, boring web pages with dynamic, real-time 3D environments. It really represents the ultimate evolution of the network, as we go from sending simple text packets over clunky copper wires on the ARPANET to navigating totally immersive, real-time 3D environments on fiber optic global networks. We really have to ask ourselves, how will this invisible infrastructure of tomorrow completely reshape the way we experience reality today? And honestly, are our current networks even ready for the massive bandwidth demands of the inner space? It is definitely something to chew on the next time you're waiting for your Wi-Fi to connect. Thanks so much for joining me on this explainer, and keep questioning how our world connects.